going to happen is when you create 2 for the next time when your push is happening, again you create a fresh node for 2. Node dot next is top. What is top? Top is 1. So 2 is now pointing to 1. Hi everyone, welcome to my channel Code with Ease by Varsha. So in one of my recent interviews, I was asked this question on how can you implement a stack using linked list. So see this very carefully. Many of us are so busy grinding the lead code questions that we often forget that how to write your own custom data structure. So this is the reason why I brought this question up. So stack can be implemented using an array, using a linked list, using a queue. So I would try to bring out all the different videos on that. But I was asked this question very deep. So no lead code question, no questions using stack, but to write your own stack class using a linked list. So first we discuss the approach and then we moved on to the code. So the code for this is available in the GitHub. Please check out from the description. Now let's move to the whiteboard to understand the approach of how can we use a linked list data structure to implement the stack functionality in that. Before we try to understand the approach of implementing the stack using linked list, let's try to do a recap of stack and linked list. So what is a stack? As we know that it is a linear data structure which follows the LEAF-4 principle, last in first out. So if I add 1, 2 and 3 to the stack, since 3 is added last, this element is going to be the first one which will be removed. Talking of linked list, it is a list of nodes which are connected to each other. The singly linked list, of course, the last node points to null, which is called the tail node. This is the head node, which is the first element of the first node, and all the nodes are connected to each other. So one node knows the memory address of another node, the next node knows the memory address of another node. Okay, so now what are the operations? So if I have to implement a stack using linked list, I also have to take care of all the operations which a stack has. That is push, adding an element, pop, removing an element from the stack, peek, to check where is the top is pointing the element, basically the element which will be popped next. And the other method can be to check if the stack is empty. So basically these are the few operations which every standard stack should support. Now when I'm writing the code using linked list, my code should work in a way so that all these operations are honored. So let's take a look one by one how will the operations be in case of a linked list. First, if we talk about the push operation. So we have to understand one thing, that because stack follows a LEAF-4 principle, one thing is clear, that if I am pushing something to the element, so if I am pushing any element to my linked list, I should make it easier for the pop operation also. Like when I want to remove the element from the linked list, it should be done in constant time. So this is what I was meaning when I say easier. The push, pop, peek, everything happens in constant time. It should not be that I have to traverse the linked list, because traversing will automatically make it a linear time complexity. So I have to make sure that the time complexity, the space complexity is honored. So let's talk about time complexity. Like I was saying, if I'm doing push, I have to make sure push happens in O1 or constant. Pop also happens constant, peek also happens in constant time, and of course is empty. So all the operations have to happen in constant time. So this is the constraint. So now let's see how does the push operation happen. So I want to push 1. So initially what I have to take is, I have to take one top variable, the most famous variable that we always talk of. Top variable, initialize it to null. So this is the initialization that is going to be done as the first step. That take the pointer top, initialize it to null. This is one thing. Next, I want to add something to my linked list. So of course I have to create a node. So I'll create a node and I'll pass the data value of 1. After creating the node, what I need to do? This node has to point to something. Initially, when a node is created for the very first time, it will point to null, and this will become the head node. So I will just say that whatever the node I've created, node.next equal to, I won't say null, because every node that you create will not be pointing to null. Eventually, when 2 will be created, 3 will be created, they will not be pointing to null. What they will be pointing to? They will be pointing to top. Now top is null, but top will change. What will it change to? So my top will be nothing but the new node that I've created. I'm just writing it as node, but I mean the new node. The first step is, this step is not going to happen in push. This is actually not the step 1. I would say this is the initialization. In Java, we use constructors. So this is just the initialization that is going to happen only one time. But in case of push operation, the first step is we have to create a node, a fresh new node, like that, however your language allows you. Next is the node next should point to top always. I'll come to that. And then we make top equal to node. What I mean by that? So now this is the node which is created, which is 1. Now next time I will create another node. So my top becomes this node. When I create the next node, think about this. Should I create the node after 1 or should I create the node before 1? Take a 5-second pause. 5, 4, 3, 2, 1. See. So the answer is I should try to create the node before 1. So my 2, the new node which I am trying to create, should be created before 1. It should be, whenever we create linked list, how we visualize it. We create one node, then we add another node in that way. It's like going in the forward direction. This case, we are going to do a backward reversal. So what is going to happen is when you create 2, for the next time when your push is happening, again you create a fresh node for 2. Node dot next is top. What is top? Top is 1. So 2 is now pointing to 1. And my new top will shift from here to here. So what it means, my current status is something like this. 2 is pointing to 1 and 1 is pointing to null, of course. So after pushing 1 and 2 in my stack, this is how my linked list structure is going to look like. Similarly, when I push 3 and 4, same thing, I'll push 3 here and similarly 4 here. So ultimately, the last node that you insert in the stack is 4 and 4 is the first node in my linked list. How does this help? Push is simple. Push is just constant in this case also because I'm just creating one node and changing the pointers. So push is definitely giving me constant time. Now, how is the pop going to be? And that is what is going to answer the question of why we did this approach. Many of you might have already guessed it. So when I'm doing the pop in stack, if 1, 2, 3 and 4 is added, 4 has to be popped first. Now, remember, always we are making the top equal to new node. So the top pointer at the end must be here. So when I want to remove it, it's very simple. I just have to say that remove the element wherever the top is, just give me that element. So it's something like return the top. The top is pointing to that node. So you just have to return the top, which means we are getting a constant time complexity. I don't have to traverse the linked list. No traversal needed. You see this? No traversal is needed in this case because if I do traversal, my time complexity will become big of n, which I don't want. If it becomes linear, I will defy my time complexity of a stack which is constant. And that is the reason I told you in the beginning that we have to make it easier for the pop operation to happen. So we push it in such a way so that the top pointer is always available to me. So now once we get the value from the top, we also have to change the top value, right? So top should go into the next node. So basically it should be, we have to capture the next node. So top should be equal to whatever the current node was dot next. So obviously you will have to store the current node initially. So we have seen how the push is working in constant time, how the pop is also working in constant time. So when the pop happens, 4 is removed. Now the top comes over here. Now it is just this much for the stack. Now if I do a peak operation, peak and pop, the only difference is we don't remove anything from this. Peak is doing what? Peak is just going to see what is there at top. What is there at top? 3. In this case, if 4 is removed, 3 is the next eligible element to be removed. And top is pointing at 3. And we can do a peak also easily. We could see what needs to be. So peak is done. Pop is also done. Push is done. What is remaining? Is empty. So how will the is empty work? That is also very simple. When do you say that the stack is empty? When it has no elements in it. When all the elements are removed one by one. So 3 is popped, 2 is popped, 1 is also popped. What will happen to my top pointer? Top will eventually come to this null. We just have to check if top is equal to null. That's it. No need of any traversal at all. So linked list based. So we used another different data structure to implement a stack. So in this way, we have seen how can we use a linked list data structure to implement our own stack. The code is already available in the GitHub. So please check out the description. So it is this simple. And this was the question I was asked in the interview. So thank you so much for watching.